Hello there, and welcome to Beyond the Cosmic. I'm so glad you're here. Maybe it's been a long day, or maybe you just like to fall asleep, thinking about stars, galaxies, and the quiet mysteries of the universe. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body rest, your mind slow down, and your thoughts drift. Because tonight, we're exploring the universe itself. Not just one galaxy or star, but the vast expanding whole. We'll move gently from fact to fact, learning about black holes, ancient light, dark matter, and distant galaxies. Some things may surprise you, others may stay with you, like a quiet thought at the edge of sleep. And if these calm explorations help you rest, feel free to like and subscribe. It helps others find their way here too. Now, if you're ready, let's begin. The universe might be older than we thought. Most current estimates place the age of the universe at about 13.8 billion years. This number is based on measurements of the cosmic microwave background and how fast the universe is expanding. But not all methods agree. Some observations of ancient stars and galaxies suggest they may be older than that estimate allows. Others question the assumed rate of expansion, or suggest that dark energy may be changing over time. These tensions haven't been resolved, and most astronomers still accept the 1388 figure. But the questions remain. Could the universe be older? Did we miss something fundamental? It's possible that what we think of as the beginning was just one part of a longer, stranger story. There are thousands of rogue planets drifting through space without stars. Not all planets orbit stars. Some are completely unbound, floating alone through the galaxy without a sun to warm them or light their skies. These rogue planets may have formed normally, then ejected from their star systems by gravitational chaos. Others might have formed on their own like failed stars. They're dark, cold, and nearly invisible unless they pass in front of background stars or glow faintly in infrared. Astronomers estimate there may be billions of them in the Milky Way, perhaps even more than the number of stars. Each one is a silent world, adrift in darkness, spinning alone in the vast spaces between. No sunrises, no sunsets, just endless night broken only by distant starlight. The universe may recycle itself through infinite cycles. The standard model of cosmology describes a universe that began with the Big Bang and will continue expanding possibly forever. But some theories imagine a different story, one where the universe goes through cycles of expansion and collapse. In these models, the universe doesn't end with a cold fade or a final crunch. Instead, it resets. After reaching a certain point, it might bounce, collapsing inward, then rebounding into a new expansion. Each cycle could wipe away the old structures, but preserve subtle traces of what came before. These ideas are speculative, but intriguing. They suggest that the universe may have no true beginning or end, just a rhythm stretched across unimaginable spans of time. one universe, giving rise to another over and over again. The oldest light we can see comes from 380,000 years after the Big Bang. Before that moment, the universe was a glowing fog, so hot and dense that light couldn't travel far without scattering. But as it expanded and cooled, it reached a turning point. Atoms formed, the fog cleared, and light was suddenly free to move. That ancient light is the cosmic microwave background, and we can still detect it today. It's the oldest direct signal in the universe, not from stars or galaxies, but from the universe itself, when it was just beginning to become transparent. The photons we observe now have been traveling for more than 13 billion years, stretched by the expansion of space into long, cool microwaves. This light is faint but ever present, a quiet glow that carries the memory of the universe's earliest clarity. Some stars have planets made almost entirely of diamond. In certain solar systems, the chemistry is very different from ours. If a planet forms with more carbon than oxygen and the pressures are high enough, something remarkable can happen. A diamond planet. Astronomers have discovered at least one such candidate, a dense world orbiting a pulsar, likely the remnant of a dead star. Based on its mass, density, and composition, the entire planet may be a crystalline form of carbon, essentially a giant diamond. It's far too hot to sparkle, and it wouldn't look like a jewel up close. But deep beneath the surface, immense carbon lattices could stretch for thousands of kilometers. These strange worlds aren't common, but they remind us how diverse the universe can be. A planet made of rock, a planet made of gas, and sometimes a planet made of crystal. The universe may have no edge, just endless curvature. It's tempting to imagine the universe as something with an edge, a border we could reach if we traveled far enough. But space doesn't seem to work that way. According to general relativity, the shape of space is determined by its contents, and current evidence suggests that the universe is either infinite or so vast and curved that it loops back on itself. If that's true, you could, in theory, travel in a straight line forever and eventually return to where you started, not by hitting a wall, but by wrapping around curved space. This is similar to how traveling around Earth doesn't reveal an edge, just a globe. The universe may work in the same way on a much grander scale, not infinite in space, but infinite in journey. The sun once had a twin, and it may still be out there. Some astronomers believe that our sun was born with a twin, a companion star formed from the same cloud of gas and dust over 4 billion years ago. Many stars forming pairs, and there's no reason to think our sun was an exception. If it existed, this lost sibling would have drifted away long ago, pulled apart by the slow gravitational tug of the Milky Way. It might still be out there, orbiting the galaxy on a different path, invisible to us now. Some theories even link this twin, nicknamed Nemesis, to mysterious extinction patterns on Earth, though there's no solid evidence for that. Still, the idea lingers that our sun, steady and alone in our sky, may once have shared its birth with a silent partner, long vanished into the stars. A raindrop of neutron star would weigh more than Mount Everest. Neutron stars are the collapsed cores of massive stars, incredibly dense remnants left behind after supernova explosions. They're only about 20 kilometers wide, but their mass is greater than the sun's. The matter inside is so densely packed that a single teaspoon of it would weigh billions of tons. If you imagined a single raindrop of neutron star material, it would be heavier than any mountain on Earth. That kind of density defies our everyday experience. Atoms are crushed together so tightly that electrons and protons merge into neutrons, forming a kind of superfluid neutron soup. Neutron stars are extreme objects, small, dark, heavy, and spinning rapidly. But in their quiet mass, they hold the memory of stellar collapse, a final state where matter becomes nearly pure gravity. Light from one galaxy can reach us from multiple directions. Sometimes light doesn't travel in a straight line. In regions of space where gravity is especially strong, near massive clusters of galaxies, for example, space-time itself curves. This curvature bends the path of light, like glass bending a beam. It's called gravitational lensing. And one of its strangest effects is that we can sometimes see multiple versions of the same distant galaxy from different angles. These images can appear as arcs, smudges, or even complete rings. They're not duplicates in space, but duplicates in vision. Different paths that light has taken through warped space-time to reach our eyes. In a few rare cases, astronomers have observed the same supernova explode more than once as its light arrived through different gravitational routes. It's a quiet reminder that in the universe, even light can get lost, take a longer path, and still find its way home. The first stars may have burned 1,000,000 times brighter than the sun. The very first stars were unlike anything we see today. Born from the pure hydrogen and helium left after the Big Bang, these stars, called population the third stars, likely formed with no metals at all, making them massive, hot, and short-lived. Some may have been hundreds of times the mass of the sun. They would have burned through their fuel quickly, shining 1,000,000 times brighter than our own star, then collapsing in spectacular explosions after just a few million years. None of these stars survive today, but their brief lives changed the universe. They created the first heavy elements, seeded galaxies with light, and set the stage for everything that followed, including us. Their light is gone now, but their fingerprints remain in the chemistry of ancient gas clouds and in the quiet structure of the early cosmos. Dark matter streams through your body as you sleep. As you lie still, dark matter flows silently around you. It's not some invisible mist. It's a form of matter that doesn't interact with light, doesn't reflect, emit, or absorb it, but it has mass, and it responds to gravity. Our galaxy is surrounded by a vast halo of dark matter. And as Earth moves through this halo, trillions of dark matter particles are thought to pass through every square centimeter of your body each second. They don't collide with your atoms. They don't leave a trace. But they're there, ghost-like, ever-present and essential. Without dark matter, galaxies wouldn't hold together. Cosmic structures wouldn't form, and the universe would be very different. We still don't know what dark matter is made of, but we know this much. It's part of your world, passing through you silently and continuously, even as you sleep. Some galaxies glow without any stars inside. In the quiet reaches of the universe, astronomers have discovered galaxies that shine but barely contain any stars. These ghostly systems are full of gas and dark matter, but show little to no evidence of star formation. Some may have lost their stars in violent gravitational encounters. Others may never have made many stars at all. A few are nearly invisible except in certain wavelengths of light, faint smudges in deep surveys of the sky. These galaxies challenge what we thought we knew about how galaxies form and evolve. If they're rich in dark matter, why haven't they built stars? If they had stars once, where did they go? These dim, quiet systems float through space like forgotten bones of cosmic history. Remind us that not every galaxy is filled with blazing light. Some simply drift unseen and unanswered. The universe has a cold spot that shouldn't exist. In the cosmic microwave background, the faint glow left over from the Big Bang. There's a patch of sky that's unusually cold. It's not just a little cooler than its surroundings. It's significantly colder and much larger than scientists expected. This cold spot spans hundreds of millions of light years, and its presence doesn't quite match the smooth randomness we'd expect from early universe physics. Some think it may be the imprint of a vast cosmic void. Others wonder if it could hint at something even stranger, like the collision of our universe with another in the very early moments of inflation. No explanation so far fully fits. The cold spot remains one of the most quietly unsettling puzzles in cosmology. Not a screaming anomaly, but a whisper that something about our universe may not be what it seems. The moon is slowly leaving us behind. Every year, the moon drifts a tiny bit farther away from Earth, about 3.5 cm. That's roughly the rate at which your fingernails grow. This slow retreat has been happening since the moon formed around 4.5 billion years ago. Back then, it was much closer, and a day on Earth was just a few hours long. The cause is tidal friction. As the moon pulls on Earth's oceans and Earth spins beneath them, a small transfer of energy gradually pushes the moon outward in its orbit. It's a quiet, relentless process, invisible on human timescales, but unmistakable over eons. In the far future, Earth and the moon may become tidally locked, always showing the same face to each other. For now, it just keeps slipping away little by little, as we spin beneath its distant glowing light. Binary stars can swap their outer layers like dancers in contact. In some binary star systems, the two stars orbit so closely that their outer layers begin to touch. As they evolve, one star can swell and spill matter onto the other, creating a delicate spiraling exchange of material. Sometimes the transfer is calm and steady. Other times, it triggers bursts of light, rapid rotation, or even a complete merger. The physics is complex, but the image is oddly graceful. Two stars locked in orbit, spinning close enough to brush and blend. One star may end up stripped to a glowing core, while the other becomes swollen and enriched. Their fates are bound together. Some of the most unusual objects in the universe, like certain supernova or compact neutron star pairs, begin as these quiet, touching binaries. A reminder that in space, even stars can share, change, and sometimes embrace. The vacuum of space is not truly empty. Even in the deepest, darkest reaches of space, far from any star or galaxy, the universe is never truly empty. According to quantum physics, what we call vacuum is a sea of activity. Tiny particle-antiparticle pairs blink into existence and vanish almost immediately. These quantum fluctuations happen all the time, everywhere, creating a kind of restless background to reality itself. They can influence the motion of particles, affect the behavior of fields, and even contribute to the energy of empty space. This is part of what gives rise to dark energy, the mysterious force accelerating the expansion of the universe. So when we picture deep space as silent and still, that image is only partly true. Beneath the quiet lies a dance of probabilities, a hidden hum of creation and disappearance, always just below the surface of nothing. Time may flow at different rates in different regions of the cosmos. We think of time as steady, a ticking rhythm that flows the same for everyone, everywhere. But in reality, time is deeply linked to gravity, motion, and the shape of space-time itself. In regions where gravity is strong, like near a black hole or a dense galaxy cluster, time slows down relative to places where gravity is weaker. This isn't just theory. It's been confirmed by experiments, satellites, and atomic clocks. But some cosmologists wonder whether time could also vary on even larger scales. Could different parts of the universe experience time at slightly different rates due to how the universe expanded in its early moments? The idea is speculative, but it opens strange possibilities. In a cosmos governed by relativity, even time may not be absolute. It may stretch, slow, or bend, quietly shaped by the space through which it flows. The Milky Way has a hidden halo that's larger than the visible galaxy. When we look at images of the Milky Way, we see a glowing spiral. Stars, dust, and gas arranged in beautiful arms. But surrounding this familiar structure is something vast and mostly invisible: the galactic halo. It's a huge sphere of diffuse gas and dark matter that extends far beyond the visible edge of the galaxy, reaching distances many times greater than the span of the disk itself. This halo contains ancient star clusters, stray stars, and vast amounts of unseen mass. It's held together by gravity, shaped by the history of collisions and mergers, and plays a quiet role in the galaxy's stability. Though we can't see it directly, we infer its presence through the motion of stars and the bending of light. The Milky Way, it turns out, is just the bright center of something much larger, a glowing heart wrapped in invisible arms. We've detected light from a galaxy just 200 million years after the Big Bang. The universe is about 13.8 billion years old, but light doesn't travel instantly. It moves through expanding space, stretched and slowed along the way. That's why we can see galaxies not as they are, but as they were long ago. Recently, astronomers using the James Webb Space Telescope identified light from a galaxy that existed just 200 million years after the Big Bang, a blink of time on the cosmic scale. That light has been traveling toward us for more than 13.5 billion years. The galaxy itself is small, faint, and primitive, but it holds clues to how the first structures formed. Observing it is like looking through a narrow window into a world we were never meant to see. The universe in its earliest chapters, when darkness was just beginning to give way to stars. The large-scale structure of the universe looks like a neural network. When astronomers map the positions of galaxies across enormous distances, a surprising pattern emerges. Galaxies aren't scattered randomly. Instead, they cluster together along thread-like filaments with vast empty regions, cosmic voids in between. This interconnected web stretches across billions of light-years and is sometimes called the cosmic web. What's eerie is that when you zoom out far enough, this structure looks uncannily like a neural network, the kind found in the human brain. Dense nodes of galaxies are like neurons, and the filaments are like axons connecting them. Of course, the resemblance is purely structural. The universe isn't thinking, but it's still quietly beautiful to consider. The largest structure we know and the one inside your own mind, shaped by entirely different physics, can end up looking so strangely alike. Stars can sing through the vacuum of space. There's no air in space, so we don't hear sound the way we do on Earth. But stars still make sound. Deep, slow vibrations that travel through their interior gases like seismic waves through a planet. These pressure waves make the star pulse and oscillate, and scientists can detect them by observing tiny changes in the star's brightness or surface motion. The field that studies this is called asteroseismology, literally the seismology of stars. Each star has its own internal frequencies, like a fingerprint determined by its size, structure, and age. By listening to these stellar vibrations, scientists can peer inside stars and learn what's happening beneath the surface. It's a kind of cosmic echolocation, a way to hear the music of stars across light years, even if the song is silent to human ears. Some stars are older than the galaxies they live in. Galaxies are not built all at once. They form over time, merging with smaller systems and drawing in stars and gas from other regions. That means some stars inside a galaxy can be older than the galaxy's current structure. They may have formed in earlier smaller galaxies that later merged into a larger one. These ancient stars often live in the outskirts or in globular clusters, tightly bound groups that orbit far from the galaxy's core. Some of them are over 13 billion years old, nearly as old as the universe itself. They carry the chemical signature of a much younger cosmos, when there were fewer heavy elements and only the simplest atoms. These stars are like fossils, quiet survivors from before the galaxy fully came together. Their light is old. Their stories began before much of what we know had even formed. There are galaxies without dark matter, and we don't know why. Dark matter is thought to be the invisible glue holding galaxies together. It explains why stars in the outer regions of galaxies move faster than expected, and why galaxies cluster the way they do. But in the last few years, Astronomers have found galaxies that seem to defy this rule. Galaxies that behave as if they have no dark matter at all. Their stars move as though only the visible matter is present. This discovery was unexpected, and it doesn't fit easily into current models. Some scientists think the dark matter was stripped away during past collisions. Others wonder if we still don't fully understand what dark matter is. Either way, these strange galaxies suggest that the universe still has secrets, and that the things we think are universal may not be so universal after all. The sun rings like a giant booming bell. Deep inside the sun, sound waves ripple through the plasma, bouncing from one layer to another, and setting the entire star into subtle, continuous vibration. These waves aren't like the sounds we hear with our ears. They're pressure waves, low, slow, and far below human hearing. But with sensitive instruments, scientists can detect them and use them to study the sun's internal structure. This field is called heliosysmology. By observing how the sun rings, scientists can map what's happening deep below the surface, its density, rotation, and even its hidden flows of hot gas. The sun, in this sense, acts like a musical instrument, vast, complex, and always playing. We just need the right tools to listen. And what we hear helps us understand not only the sun itself, but stars everywhere. Galaxies follow filaments made of something we cannot see. The universe's largest structures aren't made of stars or gas. They're shaped by something invisible, dark matter. Over billions of years, this dark matter formed enormous filaments stretching across space. And galaxies tend to form and move along these filaments, like beads on a string. We can't see the filaments directly, but we can infer them by observing how galaxies cluster and how light bends as it passes through these regions. The filaments can span hundreds of millions of light years and connect vast clusters of galaxies. In between lie great voids, nearly empty regions where very little matter exists. The dark matter filaments act like a hidden scaffolding for the visible universe, shaping how galaxies grow and where they go. And yet, we still don't know what dark matter is. The structure is there, immense, unseen, and quietly holding the universe together. Space can stretch faster than the speed of light. In normal circumstances, nothing can move faster than light. But space itself isn't bound by that rule. During the early moments after the Big Bang, space expanded so rapidly that regions of the universe were pulled apart faster than light could travel between them. This wasn't motion through space. It was the expansion of space itself. Even today, distant galaxies aren't racing away because they're moving quickly through space. They're receding because the space between us and them is stretching. And if they're far enough away, that stretching makes them recede faster than light, which is why we'll never see them again. It's not a violation of physics, but a quiet consequence of how space behaves on cosmic scales. The universe doesn't need to rush. It simply expands calmly and relentlessly beyond what we can follow. Our solar system moves through space like a helical spiral. It's easy to picture the planets orbiting the sun in neat flat circles, but zoom out further, and something stranger emerges. The sun itself is moving, orbiting the center of the Milky Way at nearly 1,000,000 km/h. As it moves, the planets follow in tow, not just circling the sun, but spiraling through space behind it. The combined motion creates a helical pattern, like a corkscrew or a twisting ribbon. Everything is in motion. The planets, the sun, the stars, the galaxy itself. There is no stillness in space, only graceful, ceaseless drift. Even as we sleep, we're tracing slow spirals through a galaxy in motion, wrapped in layers of orbits within orbits. A dance so vast we never feel it. Even nothing has a temperature. If you travel far enough from stars, planets, and galaxies into deep intergalactic space, you'll find yourself surrounded by what seems like pure emptiness. But even the vacuum has a temperature. That temperature is about 2.7 Kelvin, just a few degrees above absolute zero. It comes from the cosmic microwave background, the leftover glow from the Big Bang, now stretched and cooled by billions of years of cosmic expansion. This faint radiation fills the entire universe. No matter where you go, it's there. It's the quiet thermal signature of the early universe, still lingering, still measurable, and in the future, it will cool even further. In a few trillion years, the universe may approach absolute zero, but never quite reach it. Because even in the vastest emptiness, the echo of heat remains. Quantum fluctuations may have shaped the entire universe. At the smallest scales of reality, far smaller than atoms, the universe behaves unpredictably. Tiny random fluctuations in energy can appear and vanish in an instant due to the uncertainty built into quantum physics. And according to many cosmologists, those brief random blips may have been magnified during the universe's first moments through a process called inflation. As space expanded at unimaginable speed, tiny fluctuations were stretched to cosmic proportions. Those fluctuations became the seeds of structure, the places where matter would clump, where galaxies would form, where stars would eventually ignite. In other words, the grand structure of the cosmos, the galaxies, the filaments, the voids, may all trace back to fleeting random events at the smallest possible scale. Everything we see today, born from the trembling of nothing, Dying stars can pulse like heartbeats across millions of years. Not all stars end with a bang. Some fade more slowly, and during their final stages, they can pulsate, swelling and shrinking in rhythmic cycles. These stars, called variable stars, change in brightness over time. In some cases, the changes are steady and regular, repeating like a slow heartbeat. The pulses are caused by changes in the star's outer layers, gases expanding and cooling, then collapsing and heating up again. Some stars pulse every few days. Others take months or even years to complete a cycle. These rhythmic stars have been used to measure distances in space since their pulsation patterns relate to their true brightness. They also serve as quiet reminders that even in death, stars can keep time, not with a clock, but with a long, slow breath. Across cosmic ages, Earth is inside a giant bubble of hot gas. If you could see far into the invisible wavelengths of light past what your eyes can detect, you'd find that our solar system sits inside a vast glowing bubble of hot gas. It's called the local bubble, and it stretches for hundreds of light years in every direction. This bubble is thought to have been carved out by ancient supernova, exploding stars that blasted shock waves into the surrounding gas, heating and clearing it out. Now, our solar system drifts quietly through this low-density region surrounded by a shell of hotter gas and dust. It's not dangerous. It's not something we can feel, but it's there. A kind of quiet chamber around us, born from violence long ago, now part of the gentle backdrop of our galactic neighborhood. There's a vast, empty region behind the Great Attractor. The Great Attractor is a mysterious gravitational anomaly, a region of space so massive that entire galaxy clusters, including our own Milky Way, are slowly drifting toward it. But behind this immense concentration of matter lies something even stranger, a region known as the dipole repeller, where space appears unusually empty. It's not just a patch with fewer galaxies. It's a vast cosmic void stretching for hundreds of millions of light years. And oddly enough, its emptiness seems to push galaxies away. Together, the Great Attractor and the Dipole Repeller create a quiet gravitational tug-of-war that helps shape the motion of our local universe. We're drawn forward by unseen mass and pushed back by the emptiness beyond. It's a reminder that in the cosmos, both presence and absence can shape the path we follow. Neutrinos pass silently through the Earth and through you. Right now, trillions of particles called neutrinos are passing through your body and you'll never feel them. Neutrinos are incredibly light, neutral particles produced in enormous numbers by the sun, exploding stars, and even the early universe itself. They barely interact with normal matter. They can fly straight through a planet or your entire body without leaving a trace. Some pass through detectors buried deep underground, where rare collisions help us study them, but most simply pass through unnoticed. These particles are everywhere all the time, silently streaming through space and matter alike. They move at nearly the speed of light, and yet they almost never touch anything. The universe is full of motion, even when everything feels still. The most massive stars can collapse directly into black holes without a bang. We often imagine the death of a massive star as a violent supernova, a brilliant explosion lighting up the galaxy. But for the most massive stars, the end can be strangely quiet. Some stars are so heavy that when they run out of fuel, their cores collapse inward, and gravity wins so completely, so suddenly, that even the outer layers fall straight in. No explosion, no bright farewell, just a sudden disappearance. This process is called a direct collapse. In the moment, a star is gone, replaced by a black hole, silent, invisible, and crushingly dense. Imagine everything you've ever known, every atom, star, planet, and galaxy compressed into a single, infinitesimally small point. Everything that exists, everything that has ever existed, and everything that will ever exist, all contained in a space smaller than the smallest particle we can conceive. Then, in an instant, it all explodes outward. Time begins. Space unfolds. The universe is born. This is the story we've been told. The Big Bang as the ultimate beginning. The moment when literally everything started. But here's the question that keeps cosmologists awake at night. Is this the whole story? Because if we rewind the cosmic clock back to that first moment, before the first second ticked by, before energy cooled into matter, before even the laws of physics existed as we understand them, what was there? Was it truly nothing? A quantum vacuum seething with invisible potential? A collapsing universe from a previous cycle? A collision of higher dimensional membranes we can barely comprehend? Or something we don't even have the words for yet? Today, we're going to dig into some of the most mind-bending ideas in modern cosmology and approach the very limits of what science, and maybe even thought itself, can reach. Welcome to the ultimate question. What came before the beginning? The Big Bang. What we know. Let's start with what we're relatively certain about. And I say relatively because even our most well-established theories come with caveats. The Big Bang Theory tells us that approximately 13.8 billion years ago, the universe began in an incredibly hot, dense state and has been expanding ever since. This isn't just speculation. We have mountains of evidence supporting this model. First, there's cosmic expansion. In the 1,920 seconds, Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This suggests that space itself is expanding, like dots on the surface of an inflating balloon. If everything is moving apart now, then logically, everything must have been closer together in the past. Then there's the cosmic microwave background radiation, the CMB. This is the afterglow of the Big Bang itself, a faint whisper of light that fills the entire universe. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, this radiation is exactly what we'd expect to find if the universe started in a hot, dense state and has been cooling ever since. We also see the predicted abundances of light elements, hydrogen, helium, and lithium, formed in the first few minutes after the Big Bang through a process called Big Bang nucleosynthesis. The ratios match our predictions with stunning precision. But here's where things get tricky. The Big Bang theory describes what happened from a fraction of a second after the initial event onward. It tells us about the expansion, the cooling, the formation of matter and eventually atoms, stars, and galaxies. But it hits a wall when we try to go back to the very beginning, to time zero itself. At that point, our equations break down. Density becomes infinite. Temperature becomes infinite. The very fabric of space-time becomes so warped that our current physics simply can't describe it. We call this a singularity, not just a point in space, but a boundary where the laws of physics cease to function. So when we ask what came before the Big Bang, we're not just asking about a time period. We're asking whether the question itself even makes sense. The problem with before. Here's where we need to address something fundamental. What does before even mean? We're so used to thinking in terms of cause and effect, of one thing following another in time, that it's almost impossible to think any other way. But according to general relativity, Einstein's theory of gravity and space-time, time itself came into existence with the Big Bang. Think about that for a moment. Time isn't just a backdrop against which events unfold. Time is part of the universe. It's woven together with space in what we call space-time. If space-time itself was created in the Big Bang, then asking what came before is like asking what's north of the North Pole. The question doesn't make sense because you've reached the boundary of where that dimension applies. This was the position of Stephen Hawking and many other physicists. In Hawking's own words, asking what came before the Big Bang is like asking what lies south of the South Pole. It's a meaningless question because time itself began at the Big Bang. But not everyone is satisfied with this answer, because while it's philosophically consistent, it doesn't explain why the Big Bang happened in the first place. It doesn't explain why there's something rather than nothing. And it certainly doesn't quell our very human desire to understand the ultimate origin of everything. So scientists have developed several theories that attempt to extend our understanding beyond that initial moment. Some of these theories suggest that the Big Bang wasn't the absolute beginning, but rather a transition, a phase change in something that already existed. Let's explore these ideas, starting with one of the strangest. The concept that the universe came from nothing. Something from nothing, the quantum vacuum. When most people hear nothing, they think of absolute emptiness, the complete absence of anything. But in quantum physics, nothing is far more interesting than that. In quantum field theory, even empty space, what we call the vacuum, is never truly empty. It's seething with activity. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum itself for impossibly brief moments before annihilating each other. This isn't science fiction. It's been experimentally verified through phenomena like the Casimir effect. So here's the radical idea. What if the entire universe is just a quantum fluctuation that got out of hand? The physicist Edward Tryon proposed this in 1973, suggesting that the universe might be a vacuum fluctuation of enormous scale. Normally, these quantum fluctuations are tiny and short-lived. But under the right conditions, and we're talking about conditions that are barely comprehensible, a fluctuation could become macroscopic and last indefinitely. Here's where it gets even stranger. The total energy of the universe might actually be zero. How? Because while matter and radiation have positive energy, gravity has negative energy. When you do the math, and this is highly simplified, they might perfectly cancel each other out. If the universe has zero total energy, then its creation wouldn't violate the law of energy conservation. It would be the ultimate free lunch. But this raises immediate questions. If the universe can spontaneously emerge from quantum fluctuations, why did it happen 13.8 billion years ago and not earlier or later? And what is this quantum vacuum fluctuating in? Does it require some kind of pre-existing quantum field or space? Some physicists, like Lawrence Krauss, have argued that the laws of quantum mechanics themselves might be all that's needed, that these laws could exist without a universe for them to operate in. But this pushes the question back one level. Where do the laws of quantum mechanics come from? Others point out that this quantum vacuum isn't really nothing. It's a highly structured something with specific properties and laws. So we haven't really explained the ultimate origin. We've just moved the mystery one step back. Nevertheless, the quantum vacuum hypothesis remains one of the most scientifically grounded attempts to explain how the universe could emerge from nothing, even if that nothing is a very special kind of something. The eternal cycle. Bouncing universes. What if the Big Bang wasn't the beginning at all, but just the latest in an infinite series of cosmic cycles? This idea has ancient roots. Hindu cosmology has long described a universe that cycles through creation and destruction. But modern physics has given it new life, with what we call cyclic or oscillating universe models. The basic concept is this: the universe expands from a Big Bang, eventually stops expanding, and then collapses back in on itself in a big crunch. But instead of ending in a singularity, something happens at that moment of maximum compression. Perhaps quantum effects dominate, and the universe bounces back, triggering a new Big Bang. This cycle could repeat eternally, with each universe lasting trillions of years before collapsing and rebirthing. There would be no absolute beginning and no absolute end, just an infinite series of cosmic incarnations. One version of this is the ekpyrotic universe model, developed by physicists, including Paul Steinhardt and Neil Turok. In their model, the Big Bang was the result of two three-dimensional membranes, branes for short, colliding in a higher dimensional space. This collision released enormous energy, which we experience as the Big Bang. The branes then separate, eventually colliding again in a new cycle. These models have some attractive features. They avoid the singularity problem, the moment when physics breaks down, because the universe never actually reaches infinite density. They also provide a natural explanation for why the universe is so flat and uniform, which otherwise requires a special initial condition or the theory of cosmic inflation, which we'll discuss shortly. But cyclic models have their challenges too. For one thing, the second law of thermodynamics, which states that entropy, or disorder, always increases, poses a problem. Each cycle should become more disordered than the last, eventually leading to a heat death where no useful energy remains. How can the universe reset itself and maintain its order through infinite cycles? Some cyclic models propose mechanisms to reset entropy at each bounce, but these remain controversial and not fully worked out. There's also the question of what determines the properties of each cycle. Are they the same each time, or do the laws of physics change from one universe to the next? And if they change, what meta-laws govern those changes? Despite these challenges, cyclic universe models remind us that the Big Bang might not be the ultimate beginning. Perhaps we exist in an eternal cosmic drama with no first act, colliding brains. The multiverse in higher dimensions. Now let's venture into even stranger territory. The idea that our universe is just one of many, existing in a higher dimensional space we can barely conceive. This concept comes from string theory, which attempts to unify quantum mechanics and general relativity by proposing that the fundamental constituents of reality aren't point particles, but tiny vibrating strings of energy. Different vibration patterns of these strings correspond to different particles, electrons, quarks, photons, and so on. But here's the catch. For the mathematics of string theory to work, it requires extra dimensions beyond the 3 dimensions of space and one of time that we experience. Depending on the version, string theory requires 10 or 11 total dimensions. Where are these extra dimensions? The usual answer is that they're compactified, curled up so small that we can't detect them directly. But some versions of string theory, particularly M theory, suggest that our entire universe might be a 3-dimensional membrane, a brain floating in a higher dimensional space, called the bulk. Now, imagine that there are multiple brains in this bulk, each potentially containing its own universe with its own laws of physics. Our observable universe would be everything that exists on our particular brain. According to the ekpyrotic model I mentioned earlier, these brains can collide. When our brain collided with another, the enormous energy released manifested as the Big Bang. From our perspective, trapped on our 3-dimensional brain, it would look like the universe suddenly exploded into existence. But from a higher dimensional perspective, it was just 2 brains bumping into each other. This model explains several puzzling features of our universe. It accounts for the uniformity of the cosmic microwave background. The collision would naturally spread energy evenly across the brain. It also provides an alternative to cosmic inflation, which I'll discuss shortly. But brain cosmology raises as many questions as it answers. What exists in the bulk between brains? What determines when brains collide? Are there countless other brains out there, each with their own universes? And if so, how different are they from ours? We're now firmly in the territory where observation becomes extremely difficult. We can't directly detect extra dimensions or other brains, at least not yet. The best we can do is look for indirect signatures in the cosmic microwave background or in gravitational waves, and hope that these phenomena might give us clues about higher dimensional physics. Inflation and the multiverse. Let me introduce you to one of the most important and bizarre ideas in modern cosmology: cosmic inflation. In the 1980 seconds, physicists, including Alan Guth, realized that the standard Big Bang theory had some problems. The universe is remarkably uniform. The temperature of the cosmic microwave background is nearly identical in all directions, varying by only about 1 part in 100,000. But if different regions of the early universe were never in contact with each other, never had time for light to travel between them, how did they all end up at the same temperature? This is called the horizon problem, and inflation solves it elegantly. The theory proposes that in the first tiny fraction of a second after the Big Bang, we're talking about 10 to the minus 36 seconds, the universe underwent an incredibly rapid expansion, growing exponentially in size. During this inflationary period, a tiny patch of space, small enough that all parts of it were in causal contact, expanded to become larger than our observable universe. This explains the uniformity we see. Different regions of the observable universe look similar because they all came from the same tiny, uniform patch before inflation stretched it out. But here's where things get wild. In many versions of inflation, called eternal inflation, the inflationary process doesn't stop everywhere at once. While inflation ended in some regions, including our observable universe, it continues in other regions, spawning new bubble universes continuously. Each of these bubble universes could have different properties, different constants of nature, even different laws of physics. Some might be hospitable to life. Most would probably be sterile and lifeless. But together, they would form a vast multiverse, an infinite ensemble of universes, each with its own history and characteristics. In this picture, the Big Bang wasn't the creation of everything. It was just the moment when inflation ended in our particular bubble. The inflationary field continues to exist outside our bubble, constantly creating new universes in an eternal, ongoing process. This has profound implications. If there are infinite universes with different properties, then it's not surprising that we find ourselves in one that's suitable for life we couldn't exist in any of the others. This is an application of what's called the anthropic principle. The universe appears fine-tuned for life, because if it weren't, we wouldn't be here to observe it. But the multiverse concept is controversial. Critics argue that if we can never observe or interact with these other universes, the multiverse isn't really a scientific theory. It's not falsifiable or testable in the way that science requires. Proponents counter that the multiverse is a prediction of inflation, which is testable, and that we shouldn't reject a theory's predictions just because they're philosophically uncomfortable. The debate continues, but one thing is clear. If eternal inflation is correct, the Big Bang was far from the beginning of everything. It was just a local event in an infinitely larger and older cosmic landscape. The Hartle-Hawking no-boundary proposal. Stephen Hawking, working with James Hartle, proposed one of the most elegant and mind-bending solutions to the question of what came before the Big Bang. Nothing came before it, because there was no before. Their no-boundary proposal uses a mathematical technique called imaginary time. Now, I know that sounds like science fiction, but bear with me. In physics, imaginary numbers involving the square root of -1, are perfectly legitimate mathematical tools. Hawking and Hartle proposed that in the earliest moments of the universe, time had a different character than it does now. Near the Big Bang, time behaved more like another dimension of space. The distinction between time and space became blurred. Here's the crucial insight. If you model the universe this way, using imaginary time, the universe has no boundary in time. It's finite but boundless, like the surface of a sphere. Just as a sphere has finite area but no edge, you can travel around it forever without hitting a boundary. The universe is finite in imaginary time, but has no temporal beginning or end. When Hawking was asked what came before the Big Bang, he famously replied that the question has no meaning. It's like asking what's north of the North Pole. Time itself begins at the Big Bang, but not in a way that creates a singularity or requires a before. In this model, the universe didn't come from something, nor did it come from nothing. It simply exists as a self-contained, four-dimensional object in space-time. No creation event, no first cause, no moment of beginning. The universe just is. This is philosophically profound, but incredibly abstract. It requires thinking in imaginary time, which has no direct physical interpretation. And like many ideas we've discussed, it's extremely difficult to test experimentally. But the elegance of the no-boundary proposal has captivated many physicists. It provides a complete description of the universe that doesn't require anything outside the universe to explain it. In Hawking's own words, what place, then, for a creator? The limits of knowledge. As we've journeyed through these mind-bending theories, you might have noticed a pattern. Each explanation either pushes the mystery back one step or requires us to fundamentally rethink our concepts of time, causation, and existence itself. This raises a profound question. Are we approaching the limits of what science can tell us? Are there some questions that, by their very nature, might be unanswerable? There are several reasons why the question, what came before the Big Bang, might be uniquely challenging or even impossible to answer definitively. First, there's the observational barrier. We can only observe our universe from the inside. If something existed before the Big Bang, or if other universes exist beyond ours, we might have no way to detect them directly. The cosmic microwave background forms a kind of cosmic horizon. We can't see beyond it to earlier times, just as you can't see beyond your horizon on Earth. Second, there's the mathematical breakdown. Our current theories of physics, quantum mechanics, and general relativity work brilliantly in their respective domains, but can't be reconciled with each other. At the extreme conditions near the Big Bang, where both quantum effects and gravity are important, we need a theory of quantum gravity. Despite decades of work on string theory, loop quantum gravity, and other approaches, we don't yet have a complete, tested theory. Third, there's the conceptual challenge. Our brains evolved. Close your eyes for a moment. Imagine standing in the most remote place you can think of, perhaps the middle of the Sahara Desert at midnight, or adrift on a life raft in the Pacific Ocean, thousands of miles from any shore. Now multiply that isolation by infinity. Remove the sand, the water, the air, the warmth. Remove everything. What you're left with begins to approach the reality of the universe beyond our tiny blue planet. Welcome to a journey into the void, the cold, dark, impossibly vast emptiness that makes up nearly everything that exists. This is a story about nothing, and yet it's one of the most profound stories we can tell. Because to understand emptiness is to understand just how rare, how precious, and how utterly improbable everything we know and love truly is. I'm going to take you on a journey outward, from Earth to the edges of the observable universe, and we're going to confront a truth that both humbles and terrifies. We live on an impossibly rare island of matter and energy, surrounded by an ocean of nothingness so vast that our minds can barely grasp it. But here's what makes this story worth telling. This emptiness isn't just absence. It's a canvas, a stage, a fundamental part of what allows stars to shine and life to exist. The void is not our enemy. It's the reason we're here at all. Let's begin. Leaving home. We start our journey where all cosmic journeys must begin on Earth. Right now, as you listen to this, you're surrounded by matter. The air in your room contains roughly 25 septillion molecules per cubic meter. That's a 25 followed by 24 zeros. You can't see them, but they're there. Nitrogen, oxygen, carbon dioxide, water vapor, all bouncing around at hundreds of meters per second, colliding with each other millions of times every second. This is normal to us. This is what we call empty space, a room with nothing in it but air. But by cosmic standards, this is incredibly, almost incomprehensibly dense. Let's leave Earth's surface. As we rise through the atmosphere, something interesting happens. The air gets thinner. At the peak of Mount Everest, there's only about a third as much air as at sea level. This is why climbers need oxygen tanks. There simply aren't enough molecules to breathe. Keep going up. At the edge of space, roughly 100 kilometers above Earth's surface, the air has thinned to almost nothing. We're in what scientists call the thermosphere, where the International Space Station orbits. Here, in each cubic meter, you might find only about 100 billion molecules. That sounds like a lot, but it's 100 trillion times less dense than the air at sea level. The astronauts on the ISS float in what we call the vacuum of space, but even here, we haven't truly reached emptiness. There are still molecules, mostly hydrogen and helium, with traces of oxygen escaping from Earth's upper atmosphere. If you were floating here without a spacesuit, you'd die within seconds, but not from the vacuum itself initially. You'd die from the lack of oxygen, from the extreme cold on the dark side, from the radiation. The emptiness here can still conduct heat. It's not empty enough. We need to go farther. Interplanetary space. Let's travel to the space between Earth and Mars. This is what astronomers call interplanetary space, and it's the first time most people encounter what they think of as real emptiness. Out here, roughly 150 million kilometers from the Sun, floating in the blackness between worlds, we find something genuinely sparse. In each cubic meter of interplanetary space near Earth's orbit, there are approximately 5 million particles. 5 million sounds like a lot, until you remember that the air you breathe contains 25 septillion molecules in the same volume. We've gone from incredibly dense to almost nothing in the span of a single astronomical unit. But here's what's fascinating. This empty space is anything but quiet. The sun is constantly screaming into the void, ejecting a stream of charged particles called the solar wind. These particles race outward at speeds of 300 to 700 kilometers per second, carrying with them magnetic fields and energy. This is space weather, and it fills the solar system with invisible currents and eddies. If you were floating here, you wouldn't feel the solar wind. Directly, the particles are too sparse, too small. But if you had the right instruments, you'd detect it immediately. You'd see electrons and protons streaming past you by the billions every second. You'd register magnetic fields twisting and writhing. You'd be buffeted by shock waves from solar storms. This is the important thing to understand. Emptiness in space is relative. Even here, in what seems like perfect vacuum, there's activity, there's energy, there's something, but we're still in the sun's neighborhood. We're still in the relatively crowded space near a star. To find true emptiness, we need to venture much, much farther. The interstellar medium. Now we leave the solar system entirely. We're traveling at impossible speeds, faster than any spacecraft humanity has ever built, heading toward the nearest star, Proxima Centauri, a red dwarf 4.2 light-years away. The journey would take thousands of years with our current technology, but we're making it in moments. As we leave the sun's influence, something dramatic happens. The solar wind, which filled the space around our star, begins to falter. We cross a boundary called the heliopause, where the sun's influence ends and true interstellar space begins. The Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It's still out there, tumbling through the dark, sending back faint signals that take over 22 hours to reach Earth. This is the interstellar medium, the space between the stars. And this is where we encounter our first taste of genuine cosmic emptiness. In each cubic meter of interstellar space, there are approximately 1 million atoms. 1 million. Remember, that's compared to 25 septillion in Earth's atmosphere. We've reduced density by a factor of 25 million trillion. If the air in your room were this thin, you could count every single molecule in a space the size of a football stadium. And yet, remarkably, this isn't truly empty either. Astronomers have discovered that interstellar space is filled with all sorts of interesting things. There are clouds of hydrogen gas, some cold and dense, others hot and diffuse. There are molecules, simple ones, like carbon monoxide, but also complex organic compounds, the building blocks of life. There are dust grains, microscopic particles of silicon and carbon, and ice, leftovers from dead stars. In some regions, the interstellar medium is almost thick with this material. Molecular clouds, the stellar nurseries where new stars are born, can contain thousands or even millions of atoms per cubic centimeter. By space standards, these clouds are practically solid. They're so dense that they block starlight, creating dark patches against the Milky Way that ancient astronomers thought were holes in the heavens. But in other regions, in the bubbles blown by supernova explosions, in the voids between spiral arms, the interstellar medium thins to almost nothing. In these cavities, you might find only 1 atom per 10 cubic centimeters. That's emptier than the best vacuum chambers we can create on Earth. Picture yourself floating in one of these voids. You look around, and you see stars, thousands of them, spread across the black dome of space. But the nearest star is light years away. The light you're seeing left those stars years, decades, even centuries ago. If those stars winked out right now, you wouldn't know for years. You are truly, profoundly alone. And this is still just our galaxy. We're still in the Milky Way, still surrounded by hundreds of billions of stars. We haven't even begun to approach the real emptiness between the galaxies. Let's accelerate again, traveling now at speeds that make light itself seem slow. We're leaving the Milky Way, rising above its disk. watching it shrink from an infinite ocean of stars to a pinwheel, then to a smudge, then to a point of light. As we climb away from our galaxy, the last tendrils of matter fall away. We're entering intergalactic space. And here, finally, we encounter emptiness on a scale that defies human comprehension. In each cubic meter of intergalactic space, there is, on average, less than one atom. Less than one. You could scoop up a volume of space the size of a house, and on average, you'd find fewer atoms than there are people in a small town. This is a vacuum so perfect, so complete, that nothing we can create on Earth comes close. Let me put this in perspective. The best vacuum chambers we can build on Earth can reduce pressure to about 10 trillion molecules per cubic meter. That's phenomenally empty by terrestrial standards. You can do exotic physics experiments in vacuums like that, but it's still 10 trillion times denser than intergalactic space. If you wanted to create a volume of true intergalactic vacuum in a laboratory, you'd need a chamber the size of a planet, and you'd have to somehow remove every single atom except one or two. This is the universe at its most fundamental. This is what normal looks like on cosmic scales. The stars, the galaxies, the planets, the people, we're the anomaly. We're the weird, dense clumps in an ocean of nothingness. And this ocean is vast. The distance between galaxies is measured in millions of light years. Our nearest large neighbor, the Andromeda Galaxy, is 2.5 million light years away. Light from Andromeda takes 2.5 million years to reach us. When you look at Andromeda in the night sky, you're seeing it as it was before humans existed, before our species walked the Earth, and Andromeda is close. The average distance between galaxies in the universe is more like 10 million light years. In the great voids, the massive bubbles of empty space that thread through the cosmic web, you can travel for hundreds of millions of light years without encountering a single galaxy. Imagine that journey. You leave the Milky Way, and you point yourself toward the nearest galaxy cluster. You travel at the speed of light, the fastest speed possible, the speed at which causality itself propagates through the universe, and you travel for 10 million years. Every second, you cover 300,000 kilometers. Every year, you cover nearly 10 trillion kilometers. And for 10 million years, you see nothing. The galaxies behind you fade to invisibility. The galaxies ahead remain invisible. You are surrounded by perfect, absolute darkness, broken only by the faint glow of the cosmic microwave background, the afterglow of the Big Bang itself. This is the true face of the universe. This is what dominates existence. Not stars, not galaxies, not matter, emptiness, the temperature of nothing. But this emptiness isn't entirely cold and dead. Even in the darkest, most remote regions of intergalactic space, the universe maintains a temperature. And that temperature tells us something profound about the history and fate of everything that exists. The cosmic microwave background radiation bathes all of space in a faint glow. This radiation is the cooled remnant of the hot, dense early universe. Roughly 13.8 billion years ago, the universe was unimaginably hot, trillions of degrees. But as it expanded, it cooled. The radiation from that early fireball has been stretched by the expansion of space itself, redshifted from visible light down to microwave frequencies. Today, that radiation has a temperature of 2.7 Kelvin. That's 2.7 degrees above absolute zero, the coldest temperature theoretically possible. In Celsius, that's minus 270 degrees. In Fahrenheit, minus 454 degrees. To give you a sense of how cold this is, liquid nitrogen freezes at 77 Kelvin. Liquid hydrogen freezes at 14 Kelvin. Liquid helium, the coldest substance we can easily produce on Earth, freezes at 4 Kelvin. The cosmic microwave background is colder than any naturally occurring substance we know of. It's so cold that if you could somehow transport a thermometer to intergalactic space, it would measure the coldest temperature it's possible to measure. And yet, this radiation is everywhere. No matter where you go in the universe, no matter how far you travel, you cannot escape it. It fills every cubic centimeter of space with photons, particles of light, that have been traveling since the dawn of time. There are approximately 400 million cosmic microwave background photons in every cubic meter of space. 400 million. That sounds like a lot, and in some sense it is. It's far more than the number of atoms. But spread across the vast scales of the universe, even this is sparse. These photons are so spread out, so diffuse, that they carry almost no energy. They're the whisper of a universe that was once screaming. This is what makes intergalactic space so cold. There's nothing there to hold heat. Heat is the vibration of atoms and molecules, the kinetic energy of matter. But in a place where there's less than 1 atom per cubic meter, there's almost nothing to vibrate. You could release a tremendous amount of energy, say, from a nuclear explosion, and it would dissipate almost instantly, radiating away into the void, absorbed by nothing. In fact, this is one of the strange paradoxes of space. In the thermosphere of Earth's upper atmosphere, temperatures can reach 1,500 degrees Celsius. That sounds incredibly hot, and in one sense it is. The individual molecules are moving very fast. But if you were floating there, you wouldn't burn up from the heat. Why? Close your eyes for a moment. Imagine standing in the most remote place you can think of, perhaps the middle of the Sahara Desert at midnight, or adrift on a life raft in the Pacific Ocean, thousands of miles from any shore. Now multiply that isolation by infinity. Remove the sand, the water, the air, the warmth. Remove everything. What you're left with begins to approach the reality of the universe beyond our tiny blue planet. Welcome to a journey into the void, the cold, dark, impossibly vast emptiness that makes up nearly everything that exists. This is a story about nothing, and yet it's one of the most profound stories we can tell. Because to understand emptiness is to understand just how rare, how precious, and how utterly improbable everything we know and love truly is. I'm going to take you on a journey outward, from Earth to the edges of the observable universe, and we're going to confront a truth that both humbles and terrifies. We live on an impossibly rare island of matter and energy, surrounded by an ocean of nothingness so vast that our minds can barely grasp it. But here's what makes this story worth telling. This emptiness isn't just absence. It's a canvas, a stage, a fundamental part of what allows stars to shine and life to exist. The void is not our enemy. It's the reason we're here at all. Let's begin. Leaving home. We start our journey where all cosmic journeys must begin on Earth. Right now, as you listen to this, you're surrounded by matter. The air in your room contains roughly 25 septillion molecules per cubic meter. That's a 25 followed by 24 zeros. You can't see them, but they're there: nitrogen, oxygen, carbon dioxide, water vapor, all bouncing around at hundreds of meters per second, colliding with each other millions of times every second. This is normal to us. This is what we call empty space, a room with nothing in it but air. But by cosmic standards, this is incredibly, almost incomprehensibly dense. Let's leave Earth's surface. As we rise through the atmosphere, something interesting happens. The air gets thinner. At the peak of Mount Everest, there's only about a third as much air as at sea level. This is why climbers need oxygen tanks. There simply aren't enough molecules to breathe. Keep going up. At the edge of space, roughly 100 kilometers above Earth's surface, the air has thinned to almost nothing. We're in what scientists call the thermosphere, where the International Space Station orbits. Here, in each cubic meter, you might find only about 100 billion molecules. That sounds like a lot, but it's 100 trillion times less dense than the air at sea level. The astronauts on the ISS float in what we call the vacuum of space. But even here, we haven't truly reached emptiness. There are still molecules, mostly hydrogen and helium, with traces of oxygen escaping from Earth's upper atmosphere. If you were floating here without a spacesuit, you'd die within seconds, but not from the vacuum itself initially. You'd die from the lack of oxygen, from the extreme cold on the dark side, from the radiation. The emptiness here can still conduct heat. It's not empty enough. We need to go farther. Interplanetary space. Let's travel to the space between Earth and Mars. This is what astronomers call interplanetary space, and it's the first time most people encounter what they think of as real emptiness. Out here, roughly 150 million kilometers from the Sun, floating in the blackness between worlds, we find something genuinely sparse. In each cubic meter of interplanetary space near Earth's orbit, there are approximately 5 million particles. 5 million sounds like a lot, until you remember that the air you breathe contains 25 septillion molecules in the same volume. We've gone from incredibly dense to almost nothing in the span of a single astronomical unit. But here's what's fascinating. This empty space is anything but quiet. The Sun is constantly screaming into the void, ejecting a stream of charged particles called the solar wind. These particles race outward at speeds of 300 to 700 kilometers per second, carrying with them magnetic fields and energy. This is space weather, and it fills the solar system with invisible currents and eddies. If you were floating here, you wouldn't feel the solar wind directly. The particles are too sparse, too small, but if you had the right instruments, you'd detect it immediately. You'd see electrons and protons streaming past you by the billions every second. You'd register magnetic fields twisting and writhing. You'd be buffeted by shock waves from solar storms. This is the important thing to understand. Emptiness in space is relative. Even here, in what seems like perfect vacuum, there's activity, there's energy, there's something. But we're still in the Sun's neighborhood. We're still in the relatively crowded space near a star. To find true emptiness, we need to venture much, much farther. The interstellar medium. Now we leave the solar system entirely. We're traveling at impossible speeds, faster than any spacecraft humanity has ever built, heading toward the nearest star, Proxima Centauri, a red dwarf 4.2 light-years away. The journey would take thousands of years with our current technology, but we're making it in moments. As we leave the Sun's influence, something dramatic happens. The solar wind, which filled the space around our star, begins to falter. We cross a boundary called the heliopause, where the Sun's influence ends and true interstellar space begins. The Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It's still out there, tumbling through the dark, sending back faint signals that take over 22 hours to reach Earth. This is the interstellar medium, the space between the stars. And this is where we encounter our first taste of genuine cosmic emptiness. In each cubic meter of interstellar space, there are approximately 1 million atoms. 1 million. Remember, that's compared to 25 septillion in Earth's atmosphere. We've reduced density by a factor of 25 million trillion. If the air in your room were this thin, you could count every single molecule in a space the size of a football stadium. And yet, remarkably, this isn't truly empty either. Astronomers have discovered that interstellar space is filled with all sorts of interesting things. There are clouds of hydrogen gas, some cold and dense, others hot and diffuse. There are molecules, simple ones, like carbon monoxide, but also complex organic compounds, the building blocks of life. There are dust grains, microscopic particles of silicon and carbon, and ice, leftovers from dead stars. In some regions, the interstellar medium is almost thick with this material. Molecular clouds, the stellar nurseries where new stars are born, can contain thousands or even millions of atoms per cubic centimeter. By space standards, these clouds are practically solid. They're so dense that they block starlight, creating dark patches against the Milky Way that ancient astronomers thought were holes in the heavens. But in other regions, in the bubbles blown by supernova explosions, in the voids between spiral arms, the interstellar medium thins to almost nothing. In these cavities, you might find only 1 atom per 10 cubic centimeters. That's emptier than the best vacuum chambers we can create on Earth. Picture yourself floating in one of these voids. You look around, and you see stars, thousands of them, spread across the black dome of space. But the nearest star is light years away. The light you're seeing left those stars years, decades, even centuries ago. If those stars winked out right now, you wouldn't know for years. You are truly, profoundly alone. And this is still just our galaxy. We're still in the Milky Way, still surrounded by hundreds of billions of stars. We haven't even begun to approach the real emptiness between the galaxies. Let's accelerate again, traveling now at speeds that make light itself seem slow. We're leaving the Milky Way, rising above its disk, watching it shrink from an infinite ocean of stars to a pinwheel, then to a smudge, then to a point of light. As we climb away from our galaxy, the last tendrils of matter fall away. We're entering intergalactic space. And here, finally, we encounter emptiness on a scale that defies human comprehension. In each cubic meter of intergalactic space, there is, on average, less than 1 atom. Less than 1. You could scoop up a volume of space the size of a house, and on average, you'd find fewer atoms than there are people in a small town. This is a vacuum so perfect, so complete, that nothing we can create on Earth comes close. Let me put this in perspective. The best vacuum chambers we can build on Earth can reduce pressure to about 10 trillion molecules per cubic meter. That's phenomenally empty by terrestrial standards. You can do exotic physics experiments in vacuums like that, but it's still 10 trillion times denser than intergalactic space. If you wanted to create a volume of true intergalactic vacuum in a laboratory, you'd need a chamber the size of a planet, and you'd have to somehow remove every single atom except 1 or 2. This is the universe at its most fundamental. This is what normal looks like on cosmic scales. The stars, the galaxies, the planets, the people, we're the anomaly. We're the weird, dense clumps in an ocean of nothingness. And this ocean is vast. The distance between galaxies is measured in millions of light years. Our nearest large neighbor, the Andromeda Galaxy, is 2.5 million light years away. Light from Andromeda takes 2.5 million years to reach us. When you look at Andromeda in the night sky, you're seeing it as it was before humans existed, before our species walked the Earth, and Andromeda is close.